Plan for this recording is we're going to talk through the calculator portion of the multiple choice. So let's get rolling. Question 76. What I see is a graph of f and a bunch of comparisons between my derivative. So my first question I have to say or ask myself is, what does the graph of f tell me about the derivative? Well, I know that if my graph is increasing at a point, then the derivative is positive. So I know that f prime of a -2 is greater than 0. Okay. I know if my derivative or my graph is flat, I know then that f of 0 equals 0. And my graph is decreasing on this side, so f prime of 3 is less than 0. And now make a comparison. Which one's the biggest? The positive. So -2 would be the greatest. Everything else is less than that. 0 is less, and a negative is less than that. So answer letter D. Question 77. So this one's pretty important conceptually. You're going to see this in various ways many times on a test. So capital H, is the antiderivative of this. So if I were to integrate this, so I'm going to call this h prime, right? If h is the antiderivative of this, then this must be h prime. So the integral from where I start, or what I know, to what I want, tells me the amount of change from what I know to what I want. So what I know is h of 5. What I want is h of 2. And if I take the difference between x equals 5 to x equals 2, and I add that to my original value at 5, I'll have my answer. What I start with plus the change from what I start with to where I end is going to give me the value of h of 2. That is crucial to understand. This tells me the amount of change. The amount of change from where? From where I start. So what is down here is the value of x that I know the y value for, and the value of x I want to end up at, and this will give me the answer to my y value, or in this case, my h value. So on the calculator then, I'm going to type that in right there, except for with that expression. So let's jump over to the calculator. Can I do both at the same time? We can do both. All right, so we have pi plus, probably should have done this ahead of time. Well, I'll just keep going. Plus the integral from, now in the past, I've said you have to switch from a lower to an upper, have to go from smaller to bigger. That I said that because it has to be like that on a graph, because you can only go one direction on a graph. The calculator, with the fundamental theorem of calculus, it will do it correctly. Okay, it's from where I start to where I end. I don't need to flip these and make it a minus. You can, but I don't need to, because the calculator will handle that for me. I like this button better, so I'm going to go control. Nope, so no control. Get off the control. Yep, I knew I was going to do that. Okay, I don't want control. I want just that guy there. I like this fraction button better than divided by when I have a bunch of stuff in the numerator and the denominator. So we have x cubed. Get out of the exponent. Plus trig function sine of x. Jump down into the other expression, x squared plus 2. Taking a second just to scan to make sure I didn't type anything incorrectly. Jump up here, stick an X in there, hit enter, and we get negative 5.867, etc. Letter B. Okay, that one's super important to understand what was going on there. If you try to do the antiderivative on the test or on the calculator and then solve for the C value using this, that would work, but it's so much easier just to have a definite integral instead of an indefinite integral, because we know with sine, the calculator gives us some weird expressions sometimes. 78. The continuous function f is positive, has a domain greater than 0. Asymptotes are x equals 0 and y equals 2. So we're going to talk about the definition of an asymptote in limit notation. We're going to look at the definition of an asymptote, both vertical and horizontal, in limit notation. So I'm just going to sketch x equals 0. There's one vertical asymptote. My domain is strictly greater than 0, so I'm only looking at this side. And I have an asymptote at y equals 2. Also, the function is strictly positive, and the domain is strictly positive. So my function is strictly up here. There was a lot in those words. The continuous function f is positive, meaning my y values are positive. My graph is completely above the x-axis. The domain is positive, meaning it's in only the first quadrant. Okay, asymptotes at 0 and asymptotes at 0 and asymptotes at y equals 2. What's an asymptote? A vertical asymptote, as x approaches 0, my graph is either going to go to positive infinity or negative infinity along that vertical asymptote. As x approaches my asymptote, in this case it can only come from the right, but typically you have to check left and right, but this case it's only from the right. As I come from the right, my graph will either go to positive infinity or it will go to negative infinity. For this graph, my function is strictly positive. It must be going that direction. Can't go down here because I can't go into negatives. What does a horizontal asymptote of y equals 2 mean? The limit as x approaches infinity, because we can't go to negative, as x goes to infinity, will approach the line. So my graph is going to come here and like that. It has to. That's not totally fair. There's a couple variations, but I don't know if it really matters. But I got to say, now that I said it has to, my graph could come down, cross the asymptote, and come back up to it. Okay, that is an option, but it doesn't really matter. The limit as x goes to infinity will still be y equals 2, whether I come from the top or whether I come from the bottom. But I know it does not cross the x-axis. Why? Because of this statement here. Okay, there was a lot of setup just so we understand what limit notation is and how I got all of this from my information and how I made the graph. I'm very visual. I like seeing a picture. It helps paint 1,000 words, as they say. All right, so the limit as x goes to 0 from the right is infinity. Yep. The limit as x goes to 2, no, we're not going to 2. Okay, the limit as x goes to infinity, or 0 from the right, is equal to 2. Nope. So that one's out, that one's out. Question C, or option C, the limit as x goes to 0 from the right is equal to infinity. Yep. The limit as x goes to infinity, okay, now we're talking, is equal to 2. Perfect. Letter C. A file is downloaded to a computer at a rate modeled by the differentiable function f of t. T is in time since the download started. And f of t is measured in megabytes per second. That's important. Megabytes per second. F is already a rate of change. A file is downloaded to a computer at a rate modeled by the differentiable equation. I'm not saying that this is a differential equation. It's a differentiable equation. It has a derivative. Okay. A differential equation would look like df dt, right? It's in derivative notation. This is just saying it has a derivative. It's differentiable. Okay. Sorry, I just had to clarify some verbiage. So f is my rate of change in megabytes per second. So which of the following is the best interpretation of the rate at which the rate is changing, right? F prime is the derivative of f, which is the rate of change of the rate of change. So at time equals 5, the rate at which the file downloaded to the computer is that amount. Nope, that's what f of 5 would look like. F of 5 is the rate at which the file is being downloaded to the computer. Question B. At time t equals 5, the rate at which the file is downloaded to the computer is increasing. Okay, now we're talking about the rate at which the rate is changing, and it's increasing at a rate of 2.8. Is that true? Is it increasing? Yes, because my rate is positive. So right now I think it's B. I just want to double check and make sure I'm not missing something. Over the time interval from 0 to 5, 2.8 megabytes of file. No, this is an amount. That would be the integral. And make sure you can do this. That would be the integral from 0 to 5 of f of t. The amount is an integral of the rate. So this would be an integral of f of x dx. Over the time interval from 0 to 5, the average rate of change. Nope, that would be y2 minus y1. So that would be f of 5 minus f of 0 all over 5. No, not, you got the idea. Over 5 minus 0. You should be able to go through each of those and translate the verbiage into calculus notation or into mathematical notation like I did. There's A, there's C, and there's D. Well, this is a 5 minus 0. Fairly important skill to be able to do that, and it helps you to totally understand what you're reading. Number 80. Function f has first derivative given by that. On what intervals is the graph of f concave up? We could do this a couple ways. You could go through and you could go and graph this. So this is f prime. We want to know when is f. So I want f double prime. I'm just going to do it that way. You could graph this and find out where it's increasing, decreasing, etc. This one's an easy derivative. So this is 4x cubed minus 6x squared minus 8. That's a squared. Okay, so now this is my second derivative. I want to know on what intervals is it concave up. Okay. Yeah, I'm not sure which way I want to do it. I'm gonna graph it. We haven't done a lot of graphing. So let's grab a graph. And f of 1 looks good. So I have 4x raised to the third power, bounce over, minus 6x squared, minus 8. Ooh, I'm glad I went back and checked. My derivative is not right. That should be a 12. Hopefully you guys were hollering at me, getting my attention. Maybe it worked. You got my attention. Take the derivative correctly, Minogue. All right, so 6 times 2 is 12 minus 8. Jump back here. And it's not 12x squared. Wow, I really botched that one. But at least I caught it before we had a big mess. All right, Now I have to double check. 4x cubed minus 12x minus 8. All right. Looks good. Let's graph that thing. Hit equals. So the function f has first derivative given by this. On what intervals is it concave up? This is my second derivative. Concave up was where my second derivative is positive. Where is it positive? From 2 to infinity only. Done. It's negative down here. Never switches signs here, so that's not a point of inflection. That's a point of inflection. But this is concave up over here. X equals 2 to infinity only. Letter A. We could have solved that algebraically, and we could have found out where that's equal to 0, right? We could have solved that algebraically. So if you didn't like what I just did, let me give you a second option. That's what this is all about. Not about the fastest way. It is for you later, but not necessarily for this video. So I'm going to set that equal to 0. Sorry, excuse me. I'm going to jump over here and just do the exact same concept, but I'm going to get out of here. Go back to calculate. Let's go to menu. Let's go to solve. And we're going to solve this equation that I just typed in to the graph 4x cubed minus 12x. And if you don't like this, just fast forward and go to the next problem. Minus 12x minus 8. And I'm solving that 4x. And that's good enough. What did I do wrong? Oh, maybe I need an equals 0 in there. Let's slide over. Equals 0. Let's go equals 0. Oh, hang on. Bah. There we go, where I can edit it. And let's go equals 0. Now let's solve. So negative 1 or 2. Remember our graph. Okay, remember the graph, what it looked like. At negative 1 and at 2. So feeling pretty good. We got the right graph. We got the right solving. Sorry, excuse me. So negative 1 or 2. So which one's right? So now here's where solving is not great. I would have to go to I don't have to go to number line, but it would probably help to go to a number line then. And I would go, not that. I would go number line, negative 1, number line, why did I go to big? Number line 2. I would plug in values to the left of negative 1. I'd plug in values between negative 1 and 2. And I'd plug in values greater than 2. And I'd find out which region is positive. Totally doable. Remember our graph went like this? And so these are negative, this would be negative, and this would be positive. If I were to solve this, I would find my zeros, and I would check where my graph is then positive, which tells me concave up. And so I'd have to check to the left and right of each of those zeros, and I'd solve it that way. And that totally works. So if you're not a fan of graphing, you could do it algebraically and solve it, and then just organize your data somehow and check your results. So check left and right to find out where it's positive. Okay, that's kind of a long explanation for that question, but I think it was valuable. All right, question 81. Graph of the function f is shown above. Which of the following could be a graph of antiderivative? F is the derivative of some other function, the antiderivative, whatever we want to call that. So which of the following will this be the derivative of? So like this is the derivative and you're going backwards and finding f. Okay, so that might be easier for you. Call that f prime then, and you're looking for f. You're going backwards. The graph of f is shown. Which of the following could be the antiderivative of f? I know f prime. I want f is one way of reading that. I want to go backwards. So we could do two ways. We could just say, well, wherever this is positive, my function's increasing. So my function needs to be, or vice versa, it needs to be decreasing from a -2 to whatever that is, -1 point something. The actual graph needs to be decreasing because my derivative is negative. So this one, nope. This one, nope. This one, yep, that looks good. Decreasing from -2 to -1 point something. Decreasing from -2 to -1 point something. Okay, we have two possibilities and we have two that are out. My graph is increasing at a slower rate, increasing at a faster rate, and now it's decreased. Whoops, sorry. And now it's decreasing. So decreasing from here to here, from 1.5 to something, decreasing. Well, that didn't help. They're both decreasing. Man, sorry. So what is the difference between these two? This one here decreases from negative point something to point something. It actually decreases, which means my derivative has to go negative between these two values. That's not what we said. We said my graph is going to be increasing, but not as quickly, and then it's going to increase again, right? My graph is increasing. My derivative is positive over this entire region. So my graph of f needs to be increasing from a -1 point something to a +1 point something. The entire time my derivative is positive. It goes down to a smaller number. This might be like 2 and this is 1.8. So it's not increasing as fast, and that's kind of what this says. It's going up and it flattens just a little bit and then it keeps going back up. This little deal right here is the little bump we have coming down right there. It's still increasing. It just increases a little bit slower. Let f be the function with derivative given by that. At what value of x does f attain a maximum? At what value of f, at what value of x does f attain a maximum? So this is f prime. Where do maximums occur? Where my first derivative is 0, right? And it's going from positive to negative. So again, there's lots of options, but I'm going to explore some of the options that we really haven't done a lot in class, and I probably should do a lot more of. So I'm going to do it on this recording. And I'll show you the other way also. I'm going to do it graphically. I know some of us don't like it graphically, but that's why I'm doing it, just to show you there's other options. So I'm going to take this thing here and plug this derivative into my graph. So I'm going to go back to my home screen, go to graph. Excuse me, having problems this morning. It's early, that's why. Function, and I don't want F2. I'm going to jump up to F1, and I'm going to get rid of that whole entire thing. And I'm going to retype in fraction button, x cubed. This might be, why is it not liking me? What are you doing to me? Sorry. Technical difficulties this morning. Okay, x. There we go. Raised to the third power. I was saying some of you may not like graphing, but some of you might. So if this looks good, like something you like, go for it. What's nice is it's visual. For those of you who like seeing, a picture of what's happening. It's kind of a nice way of doing it. Square root, x cubed, maybe a little slower. I don't know. The other kind requires a little bit of work also. There's my graph, hit enter. So I can change my graph. So what did we just say? We want my derivative graph. This is my derivative graph. We want to go from positive to negative through 0. This is negative to positive. This is a minimum. This is a maximum. This is a minimum. By graphing it, man, we see it just super quickly. And I know it's a positive point something, but do I have any other positive point somethings? Looking at my options, there's only one option, and that's letter C. It's not this one. That's the minimum. It's not 0. Well, they're trying to get you to guess 0 because that's a maximum of the derivative graph. That's not what we want. We want to know where it switches from positive to negative. Letter C. Graphing is a super nice visual. You can see it really quickly. Otherwise, what do we need to do? What if I want to solve it algebraically? So then I want to know, where's my derivative 0? A fraction is 0 where the top is 0. So all I care about is when will this be 0? Don't care about when this is 0. We can see it's a -1, but I don't care about that. Okay, I want to know where is this. Well, I'm back up. Hang on. I lied. Critical values can occur where your derivative is undefined also. I do care about that. Okay, so for this point though, for the 0 part, I don't care, but being undefined does matter, and it's undefined at -1. Okay, so on the top, I would go back to my calculator. I would type in just the x cubed minus 8x squared plus 3. Find out where it's equal to 0. We're going to go back to the home screen, calculation screen, and we're going to go x cubed. No, we're not either. We're going to go solve. Now we're going to go x cubed minus 8x squared. Get out of the exponent. Minus 8x squared plus 3. And we're going to solve that for x. And we're going to throw an equals in there. Dang, I did that twice. I fixed this one faster than last time, though. You can teach an old dog a new trick. Sorry, I'm over here talking to myself. All right, so remember our graph? We went through those 3 different points. All right, remember the graph of that thing? I don't want to go back because it's just going to kill time. So now I'm going to go to a number line. And I'm going to put those on a number line. And I'm going to check left. I'm going to check right and find out which one goes from positive to negative. Okay, so before I do that, let me show you a trick on how to do that. -0.5, -0.67, -0.5. Nope. -0.5. I know it's etc., etc. 0.6, etc., etc. 7.9. Those are my values. This is a cubic, right? So instead of plugging in a bunch of values, visualize your cubic graph going through these points. When x is greater than 7.9, as x goes to infinity, this takes over and it'll be positive. We're coming from here. It's going to pass through. It's going to pass through, and it's going to go down. Where does it go from positive to negative? Right there. Whatever technique you like. I still did it graphically, but I kind of did a combination of graphing it and algebraically. You can solve it, find your 3 values, visualize your graph where it's going to be positive and negative, or actually plug in values bigger than 7.9 and see this is positive. Plug in values between here, see, oh, it's negative, and so on. Which technique is the best? The one you understand. There really isn't a better one than the one you understand. So I like the graphing one because it's quick. I like the one I just did where I solved and did a little graph. whatever you want to do is fine. Maybe try it a couple different ways. See which way is most efficient. I won't say the fastest, most efficient and giving you the right answer. Okay. Number of bacteria in a container is increasing at the rate of R. So R is a rate of increase. 100,000 bacteria at time equals 0. Which of the following expressions gives a number? Okay, remember before that H problem? Question number 77. Same problem. Remember how I said this is going to show up several times? Here it is again. The exact same setup. Different wording, same exact conceptual setup. We know time equals 0. So I'm going to integrate from 0 to 3 of R of t. And this will give me the amount of change in bacteria, the number of bacteria that have changed. I won't say increased because I don't know if it's positive or negative, but the change in bacteria from time equals 0 to time equals 3. But I have to include where we started at time equals 0. There was 1,000 bacteria. Something happened from 0 to 3. We had a change in bacteria, and the different, or the adding those together gives me the amount of bacteria after 3 hours, or at time equals 3 hours. Man, we got to get that one. That's the fundamental theorem of calculus. That shows up everywhere. Okay, question 84 is T. 85. Function g is continuous on the closed interval from 1 to 4. G of 1 is 5. G of 4 is 8. Of the following, which would guarantee there is a C in the open interval 1 to 4 where the derivative is equal to 0, or sorry, 1. Hopefully that looks really familiar. Giving you a second to think. I guess you've already thought, so I don't need to give you any more time. So I want to know when it's going to guarantee there's a number C in an open interval where my derivative is equal to 0. I keep saying that. Where the derivative is equal to 1. Hopefully it looks like mean value theorem. The average rate of change, G of 4 minus G of 1 all over 4 minus 1. The average rate of change equals the instantaneous rate of change somewhere in the interval. So this is mean value theorem. So of the following, which would guarantee? So what do we know? We know it's continuous. What does the mean value theorem if statements say? Continuous on the closed and differentiable on the open. Continuous on the closed and differentiable on the open. If that is true, then you are guaranteed by the mean value theorem that there is a point where the average rate of change equals the instantaneous rate of change somewhere in the interval. That number we call C. This is direct mean value theorem definition. Question 85, letter B. Question 86. Twice differentiable functions given up there. Those are the second derivatives given. Which of the following F, G, and H have a graph with exactly 2 points of inflection? Which of the following have graphs with exactly 2 points of inflection? So let's start scratching out ones that have more or less. Exactly 2. Okay, so this one here. Visualize this graph. Okay, this is my second derivative. What is a point of inflection? Second derivative is 0, and with big, bold, capital letters, and it switches signs at that point. Second derivative 0, and it switches signs. So at x equals 0, this graph right here is going to come down. What do we got? -2, 1, 0. These are my possible points of inflection. This is where it's equal to 0. At 0, 1, and -2. It's going to pass through -2 like a cubic. It's going to pass, nope, it's going to bounce off of the 2, and it's going to pass through the 0. It's going to come down, bounce. How do I know it's come down from the top? Why isn't it coming from here? There's no negative sign out here. So it's going to bounce off of 2. I can't talk. It's going to bounce off of 1. It's going to pass through 0. And it's going to pass through, whoa, too far, pass through that like a cubic. So it has 2 points of inflection. Okay, has 2 points of inflection. So this one's in, that one's good. What happens here? Well, this guy here is just my graph shifted up 1, right? Same graph, just shifted up 1. So we're going to go, and I guess it kind of depends on how far this dips down, right? So this is 1, this is 0, this is -2. So this graph here, probably should do that down here. 1, 0, too far. 1, 0, -2. So we kind of have to have it kind of accurate now. So it's going to come down. It's going to bounce off the 1. It's going to pass through the 0. And it's going to flatten and pass through this like such. So the question then is, when I slide this up 1, does it still have 2 points of inflection? Well, I don't know. So what I would do is I would graph that thing. Okay, and then you could also, yeah, that'd be the easiest. I'm going to just plug this into the calculator, and we're going to see what it looks like. So I'm going to go back to graph, and I'm going to go back to my functions. I'm going to go up to F1. I'm going to get rid of that mess, and I'm going to type in x, parentheses, x plus 2, nope, x minus 1. Bounce out of that thing, squared, parentheses, x plus 2. Bounce out of that thing, cubed. Sorry, I'm talking to myself. And plus 1. So let's see what does that thing look like. What did it not like? Oh, it didn't put it in right. I don't want that there. I'm gonna hit pause and get it right so you don't have to watch me do all my fiddling around. It kept throwing parentheses in the wrong spot. Okay, I think that's good. X minus 1. All right, now I hit enter. I probably didn't have to hit pause. What are you doing to me? Man, it keeps doing that. Sorry. All right, third time's a charm, maybe. Woohoo. Okay, so this is with the plus 1, right? So with the plus 1, this comes down, bounces off of this one, not a point of inflection, passes through this one, passes through this one. Okay, let's go back to our equation. I know there's a faster way than what I'm doing here, but oh, I forgot the plus 1. So that's the one I had right here. Sorry, that's the one I had right there. Let's go plus 1. What does that plus 1 do? It shifted it up, like I said, but how far? Well, it actually shifted it up so that this is no longer touching, which we would have guessed that, and these 2 points hit right here. So it hits right there and right there. Are these 2 points of inflection? Yep. They're 0, right? The second derivative is 0, and it passes through. Those are points of inflections. So right now, we have F and G. So the only thing is it H also? Is it all 3 of them? Let's just go back. And let's go up to F1, and let's change this plus to a minus. That's the only difference. Let's hit enter. Are there exactly 2 points of inflection? No, there's 1, 2, 3, 4 points of inflection now. Second derivative is 0, and it passes through, and it switches signs. So that was graphically. Yeah, I'm not sure. I'm not going to spend a lot of time trying to figure out another way of doing it, but that's what I would have done. Graph them, and it came out with F and G, letter C. Sorry, my computer or my calculator was not cooperating. I had parentheses in there, and it kept grabbing them in wrong spots. And that's all right. Okay, we're getting close. 3 more. Recording's getting kind of long again. Table of values is a function of f at selected. We have to always recognize that it's selected. We don't know what's going on between 1, 2, 3, and so on. It's a twice differentiable function. Which of the following could be true? So we're looking at the derivative, and we're looking at the second derivative, or we're looking at the derivative and whether that derivative is increasing or decreasing. So let's just look at the derivative at each of these values. 1, 2, 3, 4, and 5. Okay? So I know we don't know what's going on in between, but we could use an average rate of change to estimate mean value theorem. We can use the average rate of change to estimate the instantaneous rate of change, or the derivative. So my derivative is y2 minus y1 over x2 minus x1. 9 minus 4, 2 minus 1. This graph has a negative 5 derivative at 1. Okay, approximately. From here to here, my derivative goes 0 minus 4, so that's a negative 4 at 2. So negative 5, 4, 3, 2, 1. So negative 4. At 3, or at 3, my derivative goes to negative 3 minus 0, so it's at negative 3 at 3. And negative 5 minus 3, it's at negative 2. So my derivative is negative, right? They're all negative. It's decreasing. But it's decreasing at an increasing rate, which sounds kind of weird. My derivative is increasing. The derivative went from negative 5 to negative 4 to negative. It's increasing. My first derivative is negative and increasing. We know these are out because it's not positive. But it's negative. But the question was, is it decreasing or is it increasing? Easiest way is just to calculate a quick average and just plot the points, and you can see it's increasing. Okay. Question 88. F is a function defined by that. Let G be the function defined by that. The line tangent to the graph of F at 2 is parallel to the line tangent to the graph at G at A. Where is A? So, parallel. What is true about two parallel lines? They have the same slope, right? So I want to find the derivative of F. I want to find the derivative of G. And the line tangent to the graph of X at X equals 2 is parallel to line tangent to the graph of G at X equals A. And I want to find out what is the slope at 2 and set it equal to G and find that value. I think I said it wrong the first time. We're a little bit different. I want to know the graph of the line tangent at X equals 2. So what is F prime of 2? That's my first step. We can do it with or without a calculator. I'm just going to really quickly do it without. 1 over x squared plus 1 times 2x. Plug in 2. I get 1 over 2 squared 4, 5 times 4, so I get 4/5. Or 0.8. Okay, so now I want to take the derivative of this. x5, x to the 4th, plus 3x squared, and I want to set that equal to 0.8. If the derivative is easy, don't be super reliant on the calculator. The calculator sometimes takes some time. It's not wrong. It just takes time, and sometimes time is not what we have. So I'm going to go 5x to the fourth plus 3x squared. So I'm going to go back to my, nope, wrong one. Back to my calculation screen. Jump down here, menu, solve, and I want 5x raised to the fourth, get out of there, plus 3x squared. Remember my equal sign, comma x, hit enter, and I get negative 0.44, positive 0.44. Looks like positive 0.44. Letter C. Okay, that's pretty easy. Parallel lines, slopes are the same. Find the slope at the point they asked for. Find out what value for G has the same slope. 89. F is a continuous function for all real numbers. G is defined by that. If the average rate of change is that, which of the following statements must be true? So let me just really quickly do what we always want to do. I think we always want to do. If G is defined as an integral, let's find out what G prime is. So G prime is f of x. The average rate of change on the interval is 6. So average rate of change of G. What is the average rate of change of G? The average rate of change of G is G of 6 minus G of, G of 5. G of 5 minus G of 2 over 5 minus 2. Okay, this one's very notational, so try to, I'll just say try to focus, but obviously you're focused. Average value. So we're going to have several things we're going to plug through here and kind of talk about, which will be a great review. Average value. What's the equation for average value? 1 over b minus a. So 1 over 5 minus 2. So the average value of f is 1 over 5 minus 2, times the integral of f of x, because that's what we want to find the average value of. Average value of f is 1 over b minus a of the integral of whatever I'm trying to find the average value of. Okay, I'm integrating, from 2 to 5. What is this right here? Antiderivative of f. The antiderivative, when I take the antiderivative of f, I get g, right? Because the antiderivative of f is g. So let me change it, say it a little different also. Here's what we know right here. F of x is g prime. So I'm going to take the average value definition and just rewrite it in terms of in terms of g. So this is going to be 1 over 5 minus 2 times the integral of 2 to 5 of g prime. That makes what I just said a little easier to see. So if I take the antiderivative of g, I get f, or I get g. Sorry, not f, I get g. So this becomes 1 over 5 minus 2. Fundamental theorem of calculus says take the antiderivative of this, and I get g of x, and plug in the upper bound minus the lower bound. Right? Fundamental theorem of calc. Do this right here. Take the antiderivative of g prime, and I get g. Plug in the, we plug in the upper bound, we plug in the lower bound, and we subtract them. That and that are exactly the same thing. But it's set up by knowing that g prime is equal to f, substituting the g prime into my definition for average value, right? And knowing what we're taking the average value of f, average rate of change of g. So we're combining, we're not combining, we are comparing, there we go. We are comparing average rate of change to average value definitions. Letter A. Whoops. Letter A. I'm not sure what just happened there. There we go. All right, number 90. Which followings must be true? F is defined at x equals a. So if, what are you doing? If my function is defined at x equals a, so I'm going to call that a. Does that mean the limit as x approaches a of my function is f of a? Going back to chapter 1. Does that have to be true? Nope. If I cruise down here, open circle, keep on cruising, and this is some number 3, and I change and I define this as 7. F of a does not equal the limit as x approaches a. The limit as x approaches a of my function is equal to 3, but I'm defining f of a to be 7. This does not have to be true. F is continuous at a, so now there isn't a break in my graph. At x equals a, my graph is continuous. Then the limit as x approaches a of f of x equals f of a. There's no break in my graph. Can I draw this at any way so that my graph limit and function value is not the same? No, not possible. These have to be the same if it's, if it's continuous. Which of the following must be true? Number 2 must be true. F is differentiable. Well, that one's a no-brainer because differentiability implies continuity. If a function is differentiable, it is continuous, and if it's continuous, we just said it has to be true. So letter C. We made it. Okay. I will get this posted. Hope it helps.